Hello everyone and welcome to a lecture. Today we're going to be talking about finding the volume of what are called solids of revolution. So we talked about finding the arc length of curves and finding the surface area of a surface of revolution so far. And in today's lecture we'll be talking about finding the volume of the surface of revolution. There are a couple of different ways of doing that, and it's a little bit complicated depending on how complicated the function is. So we'll talk about first. So let's write this down. So we're going to be finding the volume of various solids of revolution. And the first thing we'll talk about is what's called the method of slicing. So the idea here is that in general we're going to have a function and that function is going to go from A to B, we'll just draw the sample function similar to how we've been drawing the sample function. Say it's this value at A, and if I revolve this function around the x-axis, we're going to get a carbon copy of the function, but it'll be upside down. We'll sort of get a picture that looks somewhat like this. So it's a three-dimensional shape. And we've already figured out how to figure out the formula for the surface area of revolution. And in this lecture we're going to talk about how to get the volume of this surface of revolution. The idea is very, very similar to what we've done kind of all along. Is we want to develop an integral formula using the definite integral, and specifically, right, it's going to depend exactly on our Riemann sums, just like every other procedure we've kind of done in this class. You see that every integral formula that you can get for geometric quantities is essentially in some way going to relate to a Riemann sum. Specifically, what we're going to be doing is we want to be able to say that, right, the total volume of this contained in this surface of revolution, we'll call it V. This is going to be approximately equal to the sum of n segments, or n smaller segments, we'll call them each Vk, where in each of these smaller segments it's approximating the volume contained in a surface of revolution of a piece of the partition. So for instance, let's say we're here and we're using a partition with a sampling point ck, we'll say, or I'll actually use xk star because that's what I used in my other video. So if xk star is the sampling point in the partition piece, xk minus 1 to xk, so this is the kth sampling partition, and the value of the function is sampled at this point xk star right here, we have an approximation at xk star to the total area under the curve in this partition piece. And if we take this and we rotate it around the x-axis, we're going to get another copy of this rectangle, and specifically we're going to get a like a cylindrical shape. So you have that on this happens on every single piece of the partition, but the VK is the volume of the kth cylindrical piece that you get when you rotate this partition, the Riemann sum partition, around the x-axis in this surface of revolution. So the idea here is that we want to be able to express VK in terms of the function and also the partition width. So this is going to rely very heavily on our basic formula from geometry, that the volume of a cylinder is the area of the cylinder multiplied by the width of the cylinder. The width of the cylinder, the kth partition cylinder, or the width of VK, which is the height of the cylinder, is equal to the width of the partition, delta xk, and the area of the base of VK is the area of a circle. It's a circle with a radius of the function value at the sampling point. So that's going to be exactly equal to pi times the radius squared, which is pi times f of the sample point squared. And this is actually all the information we need to get a correct Riemann sum here. Specifically, we take our approximation Riemann sum. This is Sn. And the Riemann sum that we get is the sum from k equals 1 to n of Vk, and the volume of the kth cylinder is going to be the width, or the height of the cylinder multiplied by the area of the base, which is pi times f of xk squared, xk star squared. So it's pi times f of xk star squared times delta xk, and then the actual volume of the surface of revolution is equal to the limit of this Riemann sum as n goes to infinity, or as the delta xk's get smaller and smaller and smaller. And the formula that you get when you take that limit is exactly the definite integral from a to b of the function pi times f of x squared dx. And this is our basic method of slicing formula that we get when we take the Riemann sum. This is also sometimes called the method of cross sections, because we're basically doing a cross-sectional slicing of the function itself, or the surface of revolution itself, and the Riemann sum. So let's go through and see if we can use this to verify some formulas and do some example problems on this using this formula. By the way, this is actually an example of a more general formula. This holds more generally for a general surface or a general shape. A more general version of this formula is if you don't have a surface of revolution, but you just have kind of like a 3D object with different cross-sectional areas. If you can somehow get the cross-sectional area as a function of the x coordinate, this is the x coordinate right here, So let's say this is some surface that may not necessarily have a a circular cross-sectional area. If you can somehow get the cross-sectional area, which is very often possible, as a function of x, say at this point right here, or at this value x right here, the cross-sectional area of the surface is a of x, then this formula is actually generalized, and you can go through this exact same procedure and generalize this approach to show that the total volume of this shape will be the integral from a to b of a of x, the cross-sectional area function dx. So this is a formula that may be useful later on down the road if you ever come up with more complicated shapes, or have like a more complicated shape that you're trying to find the volume of. But for now, we're just going to go over this formula right here and do some examples of it. So let's try and use this formula on a shape that we all know and love. We'll take the sphere. And from, say, a pre-calculus class or a high school geometry class, hopefully you know that the volume of a sphere is (4/3 pi r cubed). So you may have wondered where that comes from, why that is the way it is, and we're going to go through and do it right now. So a sphere can be thought of as the surface of revolution generated by the top half of a circle. Specifically, if we draw our circle here, say, if you take the top half of the circle and you revolve it around the x-axis, you get a copy of the circle below. Along with all of the points that are swept out when you rotate this sphere around the x-axis. And specifically, if it's a sphere of radius r, this circle has the same radius as the sphere itself, so that the distance out to the origin is just r. So the circle equation is given by x squared plus y squared is equal to r squared. And you can solve for y by isolating y squared, and then y is equal to plus or minus the square root of r squared minus x squared. And what we're interested in is just the top half, and the top half is our function f of x. So the f of x for this surface of revolution is the positive square root of r squared minus x squared. So to apply that formula that we derived before, we're going to use this f of x. You'll notice that the volume formula is a lot simpler than the arc length formula, and the surface area for surface of revolution formula in a number of different ways. First of all, the derivation was a little bit easier, and the the use of it is also easier because it doesn't depend on the derivative of f at all, which is nice. So our formula for the volume of this surface of revolution is going to be the integral from a to b. In this case, a is right here, so it's negative r, the left side of the circle, and b is positive r, the right side of the circle. So we're integrating from negative r to r of pi times f of x squared dx which is equal to, it's going to be pi times the integral from negative r to r of the square root of r squared minus x squared squared dx, which is equal to pi times the integral from negative r to r of r squared minus x squared dx. And this is a relatively straightforward antiderivative to evaluate. Specifically, the antiderivative of r squared is just r squared times x, and the antiderivative of x squared is just x cubed over 3. You have to evaluate this at the upper bound of r and the lower bound of negative r. And sure enough, when we plug into this, you get that this is going to be equal to r squared times r minus r cubed over 3. You have here minus r squared times negative r minus negative r cubed over 3, which looks kind of long, but it simplifies nicely. This is the same as this right here. So you have plus, there's going to be 2 times r cubed. And same thing here, you have negative r cubed over 3 minus negative r cubed over 3. And you have a negative sign right here as well. So the negatives cancel out, and you're left with this negative right here. It becomes negative 2/3 r cubed, which lastly, you can factor out the 2 and the r cubed, and you get 1 minus 1 cubed, which is 2 cubed. So this is exactly equal to, finally, two times pi times r cubed times 2/3, which is 4/3 pi r cubed. The exact formula that you remember, hopefully from geometry. But if not, that's okay, because we just proved it using our formula. We just solved for it using our volume formula. You can modify this formula in several different ways by taking it and, say, choosing a different axis for rotating around. Specifically, let's say you want to rotate around some constant c. Right, so instead of rotating a curve around just the x-axis, you want to rotate it around a new axis c. That's parallel to the x-axis. So this is our function right here. This is a and this is b. And instead of revolving around the x-axis, I want to revolve around, say, y equals c. That's what this blue line is right here. Well, if this is our old formula for revolving around the x-axis, we can actually change it just a little bit. Essentially, revolving it around the line y equals c changes it only a little bit. It's like doing, in some sense, a coordinate transformation where you shift everything up, and you want the new formula when you shift up by c. And when you end up doing that, specifically the formula that you end up getting is very, very similar to the other formula. It's the integral from a to b of pi times something squared, or radius value squared, but in this case the radius is now the distance from here to here if we're revolving around this axis right here, the axis y equals c. So this distance is given by c minus f of x. So it's a very, very, very small change, but it allows us to deal with more complicated scenarios. So you have a line that's shifted away from the x-axis. You can use this method for computing the volume. This is sometimes called the disk method for calculating the volume. The next formula that we have, or then the next method that we can use to find volume, the next, I guess, more complicated shape, so the next step up, is what's called, well, the method is called the washer method, but the shape is what happens when you do a solid of revolution of two separate functions. So we'll see why the method's called the washer method in a second. Let's say we have two separate functions of x. I'll color them in red and in blue. So we'll see that the top function is this function right here, and the bottom function is this function right here. And we're still going from A to B. So consider the area between these two functions. I'll shade that in green right here. If I take these two functions and I revolve both of them around the x-axis just like before, oops. We're going to get a picture that looks like this. Specifically the blue. I'll raise it up a little bit more. Where the blue function, or the lower function, is the inner function, and the red function is the outer function. And so now hopefully you can see why this is called the washer method. If you consider the area in between, or the space in between, the cross-sectional area of the shape that you get when you do this, the cross-sectional area of the shape that you get when you do this is exactly a washer. So at any given point x, a of x is the shape in the shape of a washer. It's the area of the washer the washer shape, by the way, if you're not familiar with it, a washer is exactly two concentric circles. So if you have two concentric circles, one with a smaller radius and one with a larger radius, like we do here, we have one with the radius that's given by the function, the inner function, and one with the radius that's given by the outer function. And we have that at every single cross section. So for any value of x you choose, you're going to have a different cross-sectional area. Now you can do the derivation like we did before with the Riemann sums, but what I'll do is I'm going to actually just use where is it, this formula right here, the more general form of our volume formula, to derive the formula for the cross-sectional area, or for the total volume, the volume of the surface. So the area of the washer, of any cross-section, at any point x, is going to be given by the area of that cross-sectional washer, which is the area of a washer with an inner radius, right, or inner radius of whatever the value of the lower function is. The lower function, I didn't write it down, but we'll call it g of x. And we'll call the upper function f of x. So the inner radius of this surface of revolution, or this volume of revolution, is going to be given by g of x at any given point, because it's the height of g of x, the function g of x at any given point gives you the radius of that cross-sectional washer. And likewise the outer radius is f of x, the function f of x. So the area of our washer is going to be the area of the outer circle, in this case pi times f of x squared, minus the area of the inner circle, which is pi times g of x squared. And so the volume of this shape is the integral from a to b of this cross-sectional area, the integral of the cross-sectional area function, which we already found. We found to be pi times f of x squared minus g of x squared dx. And this is the formula for the volume of this more complicated region. You could also go through and do this directly using Riemann sums, just like we did, but I like this method a little bit better because the derivation is a little bit shorter, and it directly depends only on knowing how to get the volume of a region using the cross-sectional area. So the last main thing to think about here in terms of kind of generalizing this method is what happens if we're revolving around a different axis again. So instead of revolving just around in this case we're revolving around the axis x equals 0, if we revolve around, or y equals 0, if we revolve around a different axis, what happens? How does this formula change? And it turns out it's not going to change that much, and specifically it's going to change very similarly to how it changed before. So what does the washer method look like in this case? Well, you can go through and draw a picture just like we did before. It shows when you take your function, say f of x and g of x, and instead of rotating them around the x-axis, you rotate them around some new axis. Say the new axis corresponds up here to, say, y equals c. Well, again, the picture that you get is very, very similar. You take a carbon copy and you rotate. Looks like I'm right over that, so I'm going to move this. So revolving around an axis C ends up giving you, it's a direct copy again, just like before, but the surface of revolution is around the axis x equals c. You still have a washer shape for a cross section, and now though the only thing that changes is that the radius has changed. The radius, just like before, for when we took the volume of revolution around a new axis, the radius is now going to be c minus the function. So for instance, the radius of the inner radius now is going to be c minus, right, our top functions, or c f of x minus c, so c minus f of x. That's our inner radius, and our outer radius is going to be c minus g of x. So that's that distance right there. So the formula for volume is going to be integral from a to b of pi times f of x minus c squared minus g of x minus c squared dx. And you'd have to go through, for a given example, you'd have to go through and get the volume using the inner and outer functions, the inner and outer radii, so f of x and g of x. So the idea here is that this is a very, very flexible idea. You can use this to solve for the volume of pretty much, you know, any basic geometric shape you can think of. I shouldn't say any, but many basic geometric shapes that you can think of. You can use these formulas to also do other sorts of things in, you know, specifically say in physics. Let's say you want to figure out what the mass of a region is with a distributed mass density. So I've talked about this a little bit before. Let's say we have an object, a solid object, with a specific mass density. So I'm going to finish by doing one example. Say we take the object with a mass density of a mass density function of rho of x, which is 4 minus x. Now this is measured, say, in grams per meter squared. So what this means is that along the object, at any given point along the x-axis, if you have your three-dimensional object, the cross-sectional mass density at this point along the x-axis is given by this function right here, is given by rho of x. So very often you can say have a function with a mass density that is changing in space. It changes as you move around the object. Maybe there's a lot of mass concentrated in the object right here, but say at some other point in the object, so some other cross-section, there's much less mass concentrated, or there's less mass per unit area in the cross-section. So to figure out the mass, what we have to do is figure out, again, an approximation using a Riemann sum. It's the summation from k equals 1 to n of the density of a specific cross-section at a sample point times the total area of the cross-section and you can again extrapolate this directly, the area of the cross-section, if you can approximate the area of the cross-section. So for instance, a surface of revolution has an area of its cross-section equal to the area of the circle, which is just pi times f of xk sorry, I have a typo here. It should be, because it's a three-dimensional mass density, so it has to be per meters cubed. And I also have a typo here. The density is not it's the density at the point times the volume at the point. So f of xk squared times delta xk. And in the limit, we get that the total mass of the object is equal to the limit as n goes to infinity of this Riemann sum, which is the integral from a to b of the mass density function rho of x times pi f of x squared dx. And this is the correct way mathematically of defining the mass of objects. It's the correct way to this is how you measure mass in physics. I'm going to circle this right here. So specifically, if we take this, our mass density function, and we set it up specifically, we'll say we're doing a solid from, we'll go from, a bar going from 0 to 2. Then our total mass is going to be the integral from 0 to 2. And let's specifically say it's the solid of revolution under the function 5 minus x squared. So just for argument's sake, you can really choose many different examples, but we'll do the example of this is going from 0 to 2 of the function 5 minus x squared, y equals 5 minus x squared, which at 2, 5 minus x squared is just equal to 5 minus 4, which is 1, and at 0 it's equal to 5. I'll probably put it a little bit lower. 1, 2, 3, 4, 5 right there. So it looks like that. The surface of revolution that you get when you revolve it around the axis looks like this. So this is the mass that we're looking for. This is the shape that we're looking for the mass of, and specifically we're assuming that it has a mass density of 4 minus x. So at x equals 0, the mass density is 4 when x equals 0. But as you move along the object, say when you get to 2, so at this point right here, okay, the mass density of the object is actually equal to 4 minus 2, which is 2. So as you move through this object, it becomes less dense. So the concentration of mass is more heavy in when x equals 0. So applying the formula here, we have the density is the total mass is going to be the integral of the density function, which is 4 minus x times pi times f of x squared. And f of x is 5 minus x squared dx. So this integral is going to be the exact integral. If you go through and do the integral, you're going to get the exact mass of this object in this region. And if you do this integral out and you check it out, it ends up becoming, I'm not going to do out the calculations, it's good practice to do so, but it'll be 1,474 over 15 times pi, and it's in the units of grams, because we started with grams per meter. So this is the answer to this example problem. So that's going to conclude it for this lecture. I've shown you a number of different things. I guess the only other thing that I want to mention is that all of these formulas and these methods also apply if you're rotating around the y-axis. You just need to change them a little bit. So, for instance, here, if I were to take this formula for a function being rotated around the y-axis, if you express the function as a function of y, so you could say two functions of y, or x is a function of y, and you rotate them around, right? You can take this formula and directly use this formula along the y-axis as well. It just becomes a y integral for the two functions. But this will do it for the method of slicing, and in the next lecture we'll talk about what's called the method of cylindrical shells. But thank you very much for tuning into lecture. I hope you have a nice day.